In this video, I'd like to talk a little bit about empirical molecular formulas, what they are, the difference between them, and how you can actually calculate them from pretty accessible data through laboratory experiments. And so let's just start with the definition of what these guys are. The molecular formula is the actual atoms, the actual number of atoms that are in a molecule. So for instance, you'll see on the screen I've written C6H12O6, which is the molecular formula for glucose. And many of you may remember from your biology class, it's a ring, it's a sugar ring, and you've got C's and H's and O's all mixed in there. That is the molecular formula, because if we could actually look at a single molecule of this, that's the number of each of those atoms that we would see. The molecular formula, the empirical formula, is simply the ratio of those elements to one another. So for instance, for every one carbon, I have twice that number of hydrogens and the exact same number of oxygens. So it's more of just the ratio. It's kind of the simplified thing if you think of mathematics. So my empirical formula here would simply be CH2O. And that's just the difference between them. The empirical is the simplest ratio of the elements to one another. The molecular is the actual number of atoms. Now, one small note I want to make: if you are ever dealing with ionic compounds, we deal with a formula unit, and by definition the formula unit is the empirical formula. So this really would only apply, the molecular formula really only applies to true molecules. Ionic things, generally the formula you have is an empirical formula. So let's talk about how you could calculate these things from some lab data. So if I have a compound that's analyzed and it's consistent, and again, you can do various reactions with this, and you'll do some of these in your laboratory class. I find it's made of 1.723 grams of carbon. I find it has 0.288 grams of hydrogen and 0.459 grams of oxygen. What is the empirical formula? So what is the ratio of these elements to one another? What you need to realize is that the mass, the flat-out mass, doesn't really give me a ratio, because carbon atoms, hydrogen atoms, and oxygen atoms all have different masses. So it really doesn't help me to have the mass. I need to get them into some sort of a common counting unit, because really what I'm saying is, for every one carbon atom, how many hydrogens do I have, or how many oxygens do I have? And so what I need is that common counting unit. Well, in chemistry class, that common counting unit we use is the mole. So what I need to do is turn each of these masses into moles so that I know the number of each of these things that I have, and then I can compare them. So what you do, it's pretty straightforward. You would take something like my carbon here, this 1.723 grams of carbon, and I'm going to turn that into moles. And you've done that, and that's discussed in previous videos. I'm going to go from grams of carbon to moles of carbon. 1 mole of carbon off of my periodic table is 12.0 grams. And if I do my math here, I get 0.1436 moles of carbon. Now let's do the same thing for hydrogen. 0.288 grams of hydrogen. I'm going to go from grams of hydrogen to moles of hydrogen. That's pretty easy. Hydrogen's 1. And so of course that's going to be 0.288. And that is moles of hydrogen. And then let's do that also for my oxygen, and 0.459 grams of oxygen. I'm going to go from grams of oxygen to moles of oxygen, and that would be 16.0. And if I do my math, I get 0.0287 moles of oxygen. Now, as you look at these, this is the ratio. What this is telling me is, for every 0.14 moles of carbon, I have 0.28 moles of hydrogen and 0.028 moles of oxygen. To a lot of folks, some people, you actually see there's a mathematical relationship, which can be obvious for some folks, but for others, they're like, I don't see the relationship there. If you end up with a situation where you see the ratio, you get like 0.1 to 0.2 to 0.1, it's obvious that would be a 1 to 2 to 1 ratio. But if you get numbers that are maybe not as familiar to you, easy thing to see the relationship is simply divide by the smallest of them. So if you look at my options here, I have 0.14, 0.28, and 0.028, or 0.0287. I'm going to divide by the smallest of these numbers, 0.0287, 0.0287, 0.0287. And when I do my math here, I get roughly, and it comes out very, very close, it's 5 to 10 to 1. And many of you can kind of see these if you did, without doing the math. But regardless, if I divide these out, I get 5 to 10 to 1. So what that means is my ratio is, for every 5 carbons, I have 10 hydrogens and 1 oxygen. So C5 5. That is then my empirical formula. That is the simplest ratio of these elements to one another. Now let's scroll ahead a little bit to another problem, and let me show you kind of a complication that can happen when you do what I just did. And I want to show you how to get the molecular formula with just one additional piece of information. And so what we're going to do is this. In number 47 that you see on the page, it says determine the molecular formula of a compound that contains 84.21% carbon, 15.79% hydrogen. Now, first complication is they didn't give me masses, they gave me percentages. And sometimes that'll happen when you're doing some work of this nature. But very easy, just assume you have 100 grams. If I have 100 grams of this material, then that means I have 84.21 grams of carbon and 15.79 grams of hydrogen. So just take your percentages, and just assuming 100 grams, you can turn them pretty directly then into grams. And now I'm going to do the same thing we just did. Sorry, I did that again. Grams of carbon. Now I'm going to go from grams of carbon to moles of carbon. 1 mole of carbon is 12.0 grams. And I'm going to go from grams of hydrogen to moles of hydrogen, and that's 1 over 1.0. When I take the 84.21 and divide by 12, I get 7.018, and that would be moles of carbon. And when I divide this, obviously I'm going to get 15.79 moles of hydrogen. Now, as I showed you in the previous video, if you have a situation like this and you're not totally sure of your relationship, divide by the smaller number. 7 looks like it would go into 15 about twice, but it's not exact. So let me do the math here, get the exact number. And when you do that, you get this. You get obviously 1 here when you divide by that, but here you get 2.25. So what that means is that for every 1 carbon, 1 mole of carbon or 1 carbon atom, I have 2.25 moles of hydrogen. That is my ratio. For sure that is my ratio. But of course I can't write a formula CH2.25. So how do I get around that? How do I keep that same ratio but have whole numbers? Well, recognize that when you have a situation like this, if I multiply both of these numbers by 4, of course I'm going to get a 4 here, and then up top, or on the bottom here, this is going to become a 9. That is the same mathematical ratio, but now I have whole numbers. What ends up happening then is my empirical formula would be C4H9. Now, if you end up, and I ended up here with 1 to 2.25, obviously you can see what happens. If I have 1 to 2.5, you would simply double your numbers to keep the same ratio. If I have 1 to 2 2/3, I would triple it to get rid of the thirds, or 1 1/3, something like this. So again, look at your ratio, and if it comes out to whole numbers like it did in our previous problem, you're good to go. But if you end up with something like a quarter or a half or 3/4 or a third, obviously you're going to have to multiply it to keep the same ratio. But this will allow you to then keep that ratio but have whole numbers. Now, here's the final step. So what we just did is we now have the empirical formula. That's not what they want in our problem. They want the molecular. To get my molecular, I have to first calculate the empirical, which is what I just did, and I need one additional piece of information. I need to know the molar mass. Why? Well, if you think about what the molar mass is where you take the formula of the molecule and you add up each atom, the molar mass, each atom's molar mass in that formula to get the entire molar mass. There are ways to calculate this in a lab, and again, you will see that in other videos and in some lab procedures hopefully you've done in class. But if you know the molar mass and you know the empirical formula, what you can do is this. Add up the mass of everything in your formula, your empirical formula. Carbons are 12 each. I've got 4 of them, so that's 48. Plus 9 hydrogens at 1 each gives me a mass of 57. This 57, this empirical formula mass, remember the empirical formula is a simplified ratio of my molecular formula. So what that means is my molecular formula is always a whole number multiple of the empirical formula. So if my empirical formula mass is 57 and I know my molar mass is 114, that means that my molecular formula must be twice the empirical formula. Because 57 goes into 114 2 times, that means that my molecular formula is 2 times my empirical, so it's going to be C8H18. And that is how you can go from the data, the raw data that we have, to the empirical, and then with one additional piece of information, go from that empirical to the molecular formula. Thank you very much.